Okay, so I've told you that in the visual modality, when we're reading, our brains seem to be spotting these morpheme forms off of the visual string. That seems to be one of the earliest processing stages. And it even does it in a way that it makes mistakes, like it will see a morpheme even when semantically that turns out to not be the case, like in the case of something like corner. Early decomposition happens. What about the auditory modality? The notion of morpheme spotting does not very intuitively or easily translate into the auditory modality, since in the auditory modality, the stimulus unfolds over time. So the idea that there could be this early processing stage in which you're doing some kind of morpheme stripping in a semantically blind way doesn't really make as much sense, since, for example, think about this word hearing here. If you hear hearing, by the time you get that to that boundary between the two morphemes, the R and the E, you've had a lot of time to appreciate the first part of the word, and you've probably even started to map that onto meaning. So by the time you get to the suffix, you've actually already engaged the semantic system. So in the auditory modality, things work a little bit differently. And so I just want to walk through a couple of findings that we have about morphological processing when we're actually listening to the stimuli, which is, of course, important to understand as well. So now, the general property of our brains is that they're these kind of prediction machines. We're always trying to anticipate what comes next, and the same holds in the domain of auditory language processing. So our brains are sound predictors when we're listening to language. So we're making continuous predictions about the next speech sound. So now you know that those are phonemes, and so that is something that affects our phonological categorization. And so when you get a surprising sound, a sound that you did not anticipate, that sound will drive auditory cortex more. So the kind of surprisal value of the sound modulates activity in your auditory cortex. And so here's then the finding that we have about morphological processing, and that is that if a surprising sound is part of a new morpheme, as opposed to just the next sound in the word, that actually drives auditory cortex and surrounding cortex more than just a sound that does not kind of jump over a morpheme boundary. Okay, so that kind of like probability calculation seems to pay attention to morphological structure. So that's just a list of regions in which this study by Ettinger, Linson, and Lorentz saw this kind of surprisal effect that is modulated, that is sensitive to morphological structure. So I'll walk through this with some examples. So here's a monomorphemic word, so words that just have one morpheme. There is no morphological junction to jump over. So bourbon, okay, and burble, okay. And so now these two words differ in the predictability of the last couple of sounds. So bourbon, the ending n, is more predictable, and burble at the end is less predictable, so more surprising. Okay, so that's a contrast of just how surprising the ending of the word is, and the ending is not a morpheme. So n and l, they're not English morphemes. And so then we can create a similar pair where the last two sounds are a morpheme. So these are bimorphemic words. So bruises, okay. So is here bruises is quite predictable, whereas bruiser, less predictable, okay? Bruiser, that's the more surprising ending, and it's also a suffix. Bruises, more predictable. And so the finding was a surprising ending that is just part of the sound sequence versus surprising ending that's also a morpheme. So the finding that they learned, that they discovered, was that the you get a bigger surprisal effect in auditory cortex, or more activity when you kind of cross that morpheme boundary. Okay. So there's, of course, lots to think about what that means computationally, and exactly what the process, the underlying process is that is reflected by that effect. But what we see is that these regions are sensitive to the morphological structure. Okay, so that's an example from English, obviously. And so far, we've only talked about the kind of English type morphological system where morphemes are kind of like concatenated next to each other. So it's actually a concatenative morphological system. That's the technical term for it. But that's not the only kind of morphological system that exists in the world's languages. In particular, in Semitic languages like Arabic or Hebrew, the morphemes combine with each other differently in the linear order. So instead of having like this one morpheme next to each other and so forth, the morphemes are interleaved. So this, imagine here, this would be the one morpheme. So the sounds of my fingers are representing the sounds of that morpheme. And then the other morpheme interleaves like this, okay? So now you end up with the situation where like every other sound of the word belongs to one morpheme and every other sound to the other morpheme. Okay. So that's very interesting, given these discoveries that we now have about morphological decomposition and morpheme spotting in the brain, since that kind of structure just isn't as spottable. And so sort of raises the question of whether similar findings can be observed for it in these non-concatenated languages. So I'm going to give you a bit of a flavor of that. So here's just one Arabic root, so kataba. So it's a root that has to do with writing. So if you have the kataba root sequence, you can then insert many of these vowel patterns and get lots and lots of different morphological derivatives. The root has its own Wikipedia page, so you can go ahead and appreciate all the derivatives here. So now I'm going to use the first form here, kataba, he wrote, as the example. So Laura Williams ran a study where the role of morphology in this kind of sound by sound prediction was investigated for Arabic words. So here's our interleaving, kataba, the consonants here, kataba, they're the root morpheme, it's like a writing related meaning, and then the pattern morpheme is the vowels that are interleaved. So question is, does morphological structure have an important predictive value for brain activity even in this kind of a system? So here, they're interested in whether the root plays a special role, even though it's not, an adjacent string of sounds. So here, what I'm showing is that you can compute the probability of the last root consonant just on the basis of the linear sequence of sounds, so not paying attention to morphology. So you can look at the frequency of this particular sound sequence across the entire language and compute the probability of ba given that preceding string. So that would be kind of a linear model, doesn't really look at morphology at all. Alternatively, we can compute the probability based on the root structure. So I can ask the question, what is the probability of the root kata ba given the preceding root consonants ka and ta? And now we, of course, are, that's computed across all the derivatives that employ this root. So we're not looking at the vowel sequence, that would be the pattern. So they contrasted this linear model to the morphological model and asked about the extent that those models explain brain activity. And so again, we're in this kind of auditory region, so extending a little anteriorly, but still sort of in the sylvian fissure. And what they learned is that the morphological model, in fact, is a bit more predictive than the linear model. So here we're looking at the kind of their explanatory power across time. So here we see that the red blobs represent significant results for the morphological model, and then the blue blob shows significant results for the linear model, and they both have some explanatory power, but the crucial point is that the morphological model is doing some work, and perhaps even more work than the just purely linear model. And that would be surprising if your brain just didn't know about the morphological structure at all and was just kind of monitoring for the linear sound sequence. Okay, so yes, the morphological structure does seem to matter even in this kind of a language. All right, so what we've learned is that in the visual modality, when we're reading, our brains really seem to see morphemes. That seems to be the basic mode of processing, and that seems to happen at the very earliest stages of visual word form recognition. And it even does it in a completely kind of semantically blind way, so it sees corn in corner. And in the auditory modality, our brains also seem to hear morphemes, although the processes are, of course, very different from the visual modality. And so we seem to be computing the probabilities of upcoming sounds based on morphological structure. So that's something that our brains take into account as we're computing the likelihood of encountering the next sound. So this, of course, leaves lots of questions open. For example, how exactly our brains put together the morphemes into a more complex representation in order to actually understand the full word. And that's a question that I'll return to when we learn a little bit about the neural mechanisms of composition, starting with simple cases of phrasal composition. And then we can ask the question to what extent those results extend to the morphological domain. So that's where we're going.